Hi guys, today we're going to go through pages 8 through 10 of the packet. Actually, it's going to be a little bit of page 7 and a little bit of page 8. But anyway, we're going to start here looking at this picture, which is really going to be our analogy for electricity and how it flows and how circuits work. So just take a minute, take a look at this picture and see if it would be possible in real life to have water flow in this way. So hopefully you're seeing there is a problem here. First off, what would cause the water to potentially flow? Keyword potential, because at this position up here, the water has gravitational potential energy, and then as the water flows down, it gets converted from gravitational potential to kinetic, and that would supposedly keep it flowing all the way back around while it's storing that gravitational potential again. But we know a few things about water, and it's not necessarily going to flow this way because of the direction change. So at the bottom, the water is moving this way, so there's no energy or force causing it to go back up. But imagine, if you will, if this could actually happen. So first thing we want to discuss is the current or the flow of the water. This is how fast the water is going or how much total volume of water is going by a given location a certain amount of time. That translates very well to electrical current. Electrical current isn't the flow of water in this case, but it is the flow of electricity or electrons through our circuit or conductor. So it's not necessarily how fast, but again, it's the total amount of charge per second, our coulombs per second, which we know or we define as an amp or an ampere. Something that we'll notice a lot of the units in this section of electricity are people's names. Kind of like Newton is really a kilogram times a meter per second squared. We're going to be looking at amps, ohms, coulombs, watts, volts. So sometimes it's difficult to understand what they really are. So the first thing we want to define as the flow of electricity as electrical current, or the amps moving through that conductor or circuit. Let's see. So in the electrical circuit, what is causing it to flow? Well, similar to looking at gravitational potential energy and the water moving, this is where we would have our battery, our positive side of the battery and our negative side of the battery. So this is kind of like having a bunch of positives over here, or mostly positive side, mostly negative side, and then any electron that's within our circuit or in our conductor would flow around, being pushed from the negative side and pulled by the positive side. So it's still a potential. So sometimes voltage, right, is measured in volts. It is an electric potential or potential difference of charges. So that's what a battery does. It's creating a difference in charge on different points of that battery and causing electrons within that circuit to be pulled and pushed through. So far we talked about current being measured in amps. This is the flow of electricity. Voltage, which is the potential difference or electrical potential or the differences in charge. This is like the force causing things to move. And one final thing is the resistance. So this part of our picture or circuit, we would see that the water would have to zigzag through, and this would cause the water to slow down. And that's known as electrical resistance, measured in ohms. This is determined by the material. If something is more of an insulator than conductor, then it's going to provide more resistance, or something we're not going to necessarily get into, but think of like roadways or hallways. If you have a road that has 4 lanes going in all one direction, you can have more overall traffic flow through there. And it's not as much of a resistance as, say, the same number of cars or vehicles moving through in one lane. So it's really the material and the composition of the material, the chemistry of it, and also the overall area of that material that the current's moving through. So just as in review, hopefully we see that in a circuit, that's something we didn't necessarily mention, a circuit literally means circle. So you to have a complete circuit, you have your battery here, and there needs to be a connection between the negative side of the battery going all the way around. And you would maybe have a resistor in here someplace. This might be like your light bulb. That's serving as a resistor. It's converting that electrical potential energy into light and heat. So let's take a look at our packet. A couple things that we talked about. So we're going to start off on the top of page 7. I know I said that we were only looking at page 8 to 10, but it's okay. So hopefully we see the definitions of the parts of a circuit. This is a new equation for us. This is kind of like speed equals distance over time, where I is the current, Q is the charge, and T is time. So we're looking at how much charge is moving through per time. So fairly straightforward. There's only 3 variables. So I'll walk through a few for you, and you can use your answer key in Schoology if needed. So in number 1, we have our equation. We're given that we have 3.5 amps, capital A because it's somebody's name. And we're looking for that total charge, so we're looking for Q. And it's 3 minutes, but if we remember that an amp is a coulomb per second, we need to have our time of 3 minutes and seconds. So what is 3 minutes and seconds? Nice job, Jenna. It's 180 seconds. So we just solve for Q, and we get 630 coulombs of charge. Now this is a cool thing. So part B, we're looking for how many electrons would actually be flowing through. So if we know that 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. So this is not something you necessarily need to memorize. I would provide it to you on a test quiz or an exam. So if we know the total charge and we know the charge per electron, you can look at it very conceptually and just divide the total charge by the charge per electron. So it's going to be our 630 coulombs divided by our 1.6 times 10 to the negative 19 coulombs. And we get about 3.944 times 10 to the 21 electrons. So very similar in number 2, we're going to go the opposite way to find the current. If we have 2 million electrons, and we know that each electron has 1.602 times 10 to the negative 19 coulombs of charge, and that's going to be per second. We just plug that into our calculator, and we get the overall current. In 3, we have a 60 amp hour battery. Now you're asking yourself, what the heck is a 6 amp hour battery? Should it be amps per hour? No, we're looking at the total amount of charge, or eventually total amount of energy. This is how your electric company will bill you, because they don't necessarily care how quickly you're using the electricity or the energy or the overall charge. They want to know just the total amount. So that's why it's not per hour, it's times the hours. So again, as a review, 60 amps is the same thing as 60 coulombs per second. So using our equation that we were just introduced to, we plug everything in, and it's 60 amps. We're looking for the total charge, and it's for an hour. So 1 hour is how many seconds? Good job, Josh. 3,600 seconds. And we just solve for Q, and we would get our 216,000 coulombs. And then part B again, something kind of cool. How many electrons is this? We just have our total charge divided by the charge per electron. Oops. And we would get a whole bunch of electrons. So we're going to skip the resistance part for now, just because it's a little bit difficult to go through a video, and I want to have some time for a Q&A, if we could do that later on in upcoming weeks. So here's Ohm's law. So we looked at what current, resistance, and voltage were in the beginning of this video, and this is just the relationship between the three. So we're going to actually take a moment to think way back, probably to October, and I first asked you what was Newton's second law. So what is Newton's second law? Nice, Claudia. Most people will say F equals ma. It's the relationship between force, mass, and acceleration. But if you remember, I didn't like that statement as much, because looking at this, it doesn't show independent versus dependent variables. So we rearranged it to say this. So we can see that by changing the force, we're not necessarily going to change the mass, but in this case, in the second way that we wrote it, changing the force will cause a change in acceleration. Changing the mass will cause a change in acceleration. So similarly, instead of writing V equals IR, or VIR, we're going to write I equals V over R. Because the voltage is kind of like the force, right? That's the push behind all of the current. And the resistance is kind of like the mass, right? More mass would, not result in less acceleration given the same force. So we're going to look at it that way. So we only have one problem here to work with. It's simply three variables. You're given two. You're given the current and you're given the voltage. You're just asked to find the resistance, so feel free to go through and do that and see the answer key if you need any other help. So let's see. We're going to skip some of these notes for now. We did talk about current, voltage, power. We didn't talk about power. Power is not different. Power is still the rate at which work is done, or the rate at which we are using or converting energy. So same thing as way back when. And also energy is the same as previous units. And we talked about resistance. So we have some equations here. We learned about Ohm's law, V equals IR. We did not learn about P equals IV or VI or VIP. You can feel free to go through all of the unit conversions for these three equations, and you would see they would still come out to, remember, power is measured in watts, which a watt is just a joule per second. So if you go back and do all the unit conversions, you would see that a watt in this case is still a watt, and that's just converted from coulombs per second, and looking at energy to get joules, but I don't think there's no need to go through that. So you have, again, some very simple calculations for what I would consider an honor student. So go through each one using the equation, just like in the beginning of the year, use that guess method. What variables do you have? So in like number one, you have a voltage and a current, and you're looking for the power. So find the correct equation that you would use for that. So go through. If you need help, take a look at the Schoology notes. And I think that is pretty much it for the day. If you can do pages 8 through 10, and you have no questions, you're set. If not, send me a Schoology message.